could stretch the filing time 2.5 hours, you know, so you had to stretch it to 3. Possibility does exist that in the exam room to which we can assign, which is Sterling, maybe there's nobody coming in there after us. I don't, however, consider this to be a problem because the folks who have been proctoring the exam since I've allotted 3 hours are telling me that just about no one needs anything close to 3 hours. So that's good. Final will be 26 questions rather than 24. And after I write it, which I haven't started to do yet, I'll post information regarding such on the Sakai website. With good fortune this Friday, for those of you who attend the review that I plan, I'll be able at that time to share information with you about the nature of the beast. So as I told you, I expect to run a review this Friday, starting with time concurrent with our class time, extending for period 6 in Floyd, 100. Floyd's right over here. Small building right next to the east side of the hall. Shouldn't have any trouble finding it. On the first floor, it's a nice room. I expect also to have with me, in my hands, the solution keys to each of the exams we tackle this term, plus the solution keys to F12, SP12, F11, SP11, F10, SP10 finals. Now, I think that's enough. This way, if you ask a question regarding the review activity, which relates to a specific question or problem from a past exam, you can tell me which exam and which question or problem, so I can go straight to it. And if you ask something other than this, I'll do what I can with it. After all, when many of you folks come around and you talk about a question or a problem on an exam or quiz, and you talk about what they want, I am they. I wrote all of these things. Every one of them. Every exam which I invent is new. I've told you this before. I detest using past exams. It gets my mind stale and gives an ever obvious advantage to anybody who's had the past exam in their possession and has reviewed such in preparation for the coming exam. That stuff doesn't do anything good with me as far as memorizing answers to past exams. Because I don't use them. But I think you know that. All right, let's get at the last things we wish to wrestle with in chapter 24, which in the main are stereochemical in nature, boron complexes, which show geometric isomerism and possibly optical isomerism. The complex is chiral, which we defined last time. And then another stereochemical issue. Ring strength. Now, regarding questions 2418 and 2419, I told you at the conclusion of our last conversation to take a look at these. I first asked if this complex is geometrically simpler or more complicated. Is this complex more symmetrical or less symmetrical? In this complex, whose isomers we considered last time, and in so doing found out that the all-cis geometric isomer for this complex is chiral. Now, what did you discover? You worked on it? I guess I won't answer Take them. If you see a complex which compositionally is similar, clearly these complexes are compositionally similar, because they're each composed of the same types of ligands. 3 sets of different monodentate ligands, A, B, C. Could be ammonia molecules, water molecules, chloride ions, cyanide ions, and a whole slew of monodentate ligands. If one of the 2 complexes, like this one, has 3 rather than 2 of a particular ligand, and the remaining ligands are of 2 types rather than 3 types, this complex is more or less the same, symmetrically speaking. The answer is discovered by seeing if this thing has more isomeric variation than this thing. What did you find out? Would you try it? Well, I suggest strongly you try this stuff before you find it. A lot of this kind of stuff on the planet. Because structure is the most important property of any species. You've heard that before, haven't you? So let's look at this one and consider the least symmetric variant. Which means the remaining A ligand will be here or here, or here or here. Because if the remaining A ligand is here, then I have 2 A ligands which are trans, just as if I put A here. But if I put A or A here, then all the A ligands are cis. And we have a facial orientation of A ligands. But if I put the A ligand here or here, I have a meridional orientation of A ligands, which is of lower symmetry. Facial or meridional? All right. I accept that. Now, get this out of my way because I want to draw pictures. BBC. Clearly, when I now put in BBC, they all have to occupy with respect to each other cis coordination position. So I'll just put them in. Doesn't make any difference how you scatter them. You can draw pictures to prove it. B is here, B is here, this is our mirror. A is here, A is here, A is here, C is here. Let's rotate. B goes here, A goes here, B goes here, A goes here. And of course I did the rotation by holding the axially oriented top and bottom ligands, which in this case are A and C respectively. Looks the same to me. And this is the least symmetric variant of this complex. So what would you say now? Which complex is of lower symmetry? A2, B2, C2, or this thing? Which one has more isomeric variation? A2, B2, C2, or this thing? Which one? A2, B2, C2 by far. When you start building up the number of ligands which are the same, you up symmetry considerably. Now I know you're just hearing about this for the first time, so I'm sympathetic with your inability to immediately catch a hold of this stuff. But if you sit down with a piece of paper and pencil and draw pictures, you'll find out a lot. That's what you got to do. Or as I said, better yet, especially for those of you who are going on to study more chemistry, which I'm sure is most of you, get a model set. very valuable to. So, when I start making the number of possible geometric isomers for this, I've looked at this. It's a mirror image. The mirror image is the same. So let's get this out of the way. All A cis, A's meridianal. How many geometric isomers can I now construct with the A's meridianal? 2, B, B, C, or B, C, B. And you can put it in these. Let's look at this one. Directed, as I told you for the bonus quiz, which, remind you again, is due at this gathering. So even if you are not of a mind to stay for the review, if you want credit for the bonus quiz, I recommend strongly you bring it forth at this time. Because come 11:46 a.m., I'm not accepting any more bonus quizzes. You think that one's optically active? Well, at a glance, you should see if this is optically active, then this is optically active. You think these are optically active? Whenever you see a feature which corresponds to a high degree of symmetry, it immediately is essentially a guarantee that this is not optically active. Now, this feature or aspect of symmetry to which I refer is called a plane of symmetry. Center of symmetry, but plane of symmetry will cover all cases. I don't know that I want to take time to draw pictures to illustrate planes of symmetry. But I think I referred you to one of the bonus quiz that I asked students to consider on a previous bonus quiz. If for this complex or this complex, I don't want to take time to construct a loop. So let's say that these two white model parts each constitute nitrogen donor atoms, and here is the ethylene diamine. So if I'm going to complete this, I do this because we've shown for each of these a set of 2 monodentate ligands, which are trans. The remaining 2 monodentate ligands are cis. Now, see if you can see this. I'm going to take a saw and I'm going to cut this thing this way, right through here. See where I'm cutting it? This way. And I'm going to cut right through this ethylene diamine ring. Cut right through it. All right? Cutting this way. There's the plane symmetry to which I refer. Now here's my mirror where I had that saw. Notice that in the mirror, this will see this. All the stuff on this side of the ring will see all the stuff on this side of the ring, and what we'll see here is identical to what we'll see here. And here I cut right through a green atom. So I got half a green atom on this side of where I made the cut, where the mirror is. The other half here. Same for the center atom, same here. Do these parts look to be identical to each other? Do you think this is optically active? Not at all. Because these mirror parts are identical. So this plane of symmetry to which I've referred, regarding the pictures that I have on the board, it's cut through here. Cut through here. The plane goes like this. Saws this way through B, this way through B. And remember, this is a canted square, and that is cut right through this canted square. Here's where I made the cut. Right through there. So, what I've looked at here are two geometric isomer variables for this. Now let's look at this. Please recognize that when you have one bidentate chelating ligand, for the different pictures you want to draw of this, like we're doing on the board, keep the chelating ligand in the same place all the time. Otherwise, you'll get yourself confused because you're not familiar with this stuff yet. Because this is nothing but an object that can be blown around in the wind. If these two white atoms constitute the nitrogen atoms or ethylene diamine chelating ring, well, it's all over the place. I can make this chelating ring any orientation I want. That doesn't change anything. What's the remaining possible geometric isomer for this? Like ligands, cis and trans, like ligands, cis and trans. And I make it so like ligands are exclusively trans to each other? That's impossible, because these coordination positions are cis to each other. But can I make it so like ligands, each set of two like ligands are cis to each other? Would it matter if I had B, B, A, A? Would it matter if I had B, B, and B, 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 and A? Does that matter?
Yes.
No, that would matter. Let's see why. Do you agree this is the least symmetric of the geometric isomers for this stuff? Because all like ligands are cis. Of course, the ethylene diamine ring, if I haven't not mentioned this, it's in the notes. I hope you recognize this, but if not, let me point it out. These chelating ligands can only, for two adjacent chelating atoms, connect cis, but not trans coordination positions. You see why? What would be wrong or impossible about this? Keeping these as nitrogen atoms part of the ethylene diamine ring. Keeping also in mind that we don't have these sticks where bonds really are. These atoms are smushed into, the electron clouds of these atoms are smushed into each other. What's impossible about this? You know, between NH2 and NH2, there's CH2 and CH2. And these are physical entities. They take up space. Where's the space? If they try to go this way, they're going to bump into this. They try to go this way, they bump into this. It's sterically impossible. Now, if I had a tridentate chelating ligand, does that one sound familiar? to trans coordination positions by this. Because these two positions are cis, just like these two positions are cis. Or I can go here to here. Or I can go here to here. These positions are trans. But each adjacent pair of donor atoms are connecting cis coordination positions exclusively. Back to this. There's the mirror image. Is this, which is the mirror image of this, is this the same as this? Are these superimposable? No. Well, let's play the game. Now the ring is over there, just like that. A's up here, just like that. B's down here, just like that. But where did this B wind up? 180-degree rotation puts it here. And 180-degree rotation of this A puts it here. So this is what I was talking about when I used all these words and got you confused, and I looked at this and I said, what if I put A here and A here and B here and B here? Do that. That is different from this, isn't it? So we've shown that this, which is the same as this, are each different from this. These are the mirror image of this. In this case, the mirror images are not superimposable. So this stuff has lower symmetry than this stuff, because this stuff has an isomer which is optically active, whereas this stuff does not. Now let's have more fun. I told you about this word. Somebody looked it up. Somebody followed my directives. Shall I take off 100 points for everybody who didn't follow my directives? For those who did, the score stays the same. I only penalize those who don't follow. Those who did what I said, they remain neutral. But those who didn't, I either hit them with strong acid or strong base. In either case, you get burned. Right? Isn't that fair? Ethylene diamine. Let's do some chemistry on an ethylene diamine molecule. And take a hydrogen atom from either terminal nitrogen, it doesn't make any difference. And in one case, replace hydrogen with CH3. The second case, let's replace hydrogen with a fluorine atom. Now, these are still obviously chelating ligands. How would this as a donor compare strength-wise with this as a donor? How would the liganding ability of this compare to the liganding ability of this? Which of these is the better sigma bonder? How about this? You learned about this stuff yesterday. You remember learning about this stuff yesterday? Did you, for example, come to grips with understanding why ethylene diamine is a somewhat stronger sigma bonder than the ammonia molecule? That makes the difference. How many remember this word? Induction. are these molecules as ligands of equal sigma donor strength? Which one's better? EN or this fluorine substituted EN? Which one is better? EN. Hey, this thing is substantially electronegative. I mean, this is the atom of greatest electronegativity. Therefore, it draws electron density substantially by induction. What impact will that exert on the ability of this nitrogen atom to use this non-bonding pair to make a sigma coordinate covalent bond? Will this strengthen that ability or detract from that ability? Detract. Now, how about this? This is specifically what you were talking about yesterday regarding the difference between ethylene, diamine, and ammonia molecule. Here, I've taken a hydrogen atom and replaced it with a methyl group. Is this a better sigma donor, a poorer sigma donor, or an equal strength sigma donor as this? Which one? What, is this one better? You betcha. Why is it better? Statement. If you go to the laboratory, this is called methylamine, because it's ammonia molecule with a methyl group stuck to it, rather than ammonia. Which one of these will make stronger bonds with H+? This one. What's that tell us? That tells us a methyl group compared to a hydrogen atom is electron withdrawing or electron releasing? Electron releasing. Electron density releasing. This thing magnifies the negative charge density of this non-bonding pair relative to hydrogen. This is a better ligand, and it's a better Bronsted base. It bonds more strongly to H+. You do stuff like this all the time in organic life. All right, let's take away another hydrogen, put in another methyl group. How about the sigma donor strength of that thing compared to each of these? Better yet, but be careful, more organic. At this stage of the game, if I did this, I would expect you to predict this to be the best sigma donor of these that we have considered. But this one is a little bit weaker than this one, because this one leads to steric hindrance. Because you've got all these bulky methyl groups wrapped around this nitrogen atom, which impedes its ability to use this electron pair to make bond. You just can't get away from this structure stuff. But at this stage of the game, if I ask this, you say this is better, because methyl groups are better, are electron releasing relative to hydrogen atom and IP atom. Well, let's see that one. Let's instead look at these ligands, these two. We talked about the donor strengths. Now let's look at them from a stereochemical standpoint, diastereomeric standpoint. What can you tell me about this nitrogen atom? What can you tell me about this nitrogen atom? Regarding its stereochemical character relative to this nitrogen atom, or this nitrogen atom, or this nitrogen atom, or this nitrogen atom. How does this nitrogen atom and this nitrogen atom, how do these two nitrogen atoms, the one with the new substituents on, methyl here, fluorine here, stereochemically, how do these nitrogen atoms compare to the NH2 nitrogens? All right? The blue part's the nitrogen. The blue part's the nitrogen. The red loops are, of course, the non-bonding pairs. They like to bond noggin because my noggin is a metal thing. So these are each recognizable as substituted ammonia molecules. If we let the blue thing become hydrogen, then the red or the purple thing can be a methyl group and the green thing can be a chlorine. Are these stereochemically identical? Or are these nitrogen atoms chiral? Let's find out. Do they look like mirror images? Mirror images. Are they superimposable? Well, let's find out. Blue on blue, purple on purple, and uh-oh, look what we got here. Mirror images. Chiral. So guess what happens to the stereochemistry of coordination complexes? If I do something like this. If I take an ethylene diamine molecule, take it to the chemistry laboratory, and operate on one of the nitrogen atoms so as to replace no more than one hydrogen atom with a different atom or group. This is a nitrogen atom which is now connected to 3 different things, isn't it? Actually 4 different things. A non-bonding pair, an H, a methyl, and all this stuff. Like your model. Non-bonding pair and 3 different things. Nitrogen atom, non-bonding pair, and 3 different things. H, methyl, this. If I use this as a ligand, what does that guarantee about the stereochemistry for any complex that I make using this as a ligand? It's got to be optically active, doesn't it? Because it's got a chiral nitrogen in it. How about that? And now the stereochemistry has got to be a lot more fun. Let's take a look at these models. You see the obvious similarities in these 2 molecules? One, two, three, four identical monodentate ligands. Identical central atoms. They're each silver and cerulean. Okay. And each are chelated with a ligand that's got a white donor atom, bigger than these things. Just happen to be the parts I have. A blue donor atom, and on the blue donor atom, I got one of these white atoms and a red atom. White, red. How about that? Does this chelating ligand stereochemically resemble what we have on board? Here's my blue donor atom. Is this blue donor atom chiral? Is it connected to 1, 2, 3, 4 different groups? Just like the model we just showed you. So when you deal with complexes like this, the stereochemical considerations magnify considerably. Let's see how these 2 models compare to each other. Let's hold it this way. What do you say about these? Are they mirror images? Yeah, they're mirror images. And we we have recognized that this nitrogen donor atom, this nitrogen donor atom, these are carbon nitrogens. So if these are mirror images, are they superimposable? No. Let's take a look. If I overlay all the monodentate ligands, they all wind up being in the same position, except my hands are too big. For this monodentate ligand on this complex, which now is this monodentate ligand on this complex with this white donor atom, which is part of our chelate. Interesting. These are not superimposable. Now then, the $64 question. If I go to these ligands we have on the board, see this? Are these the same? Now, to interconvert these, that's easy. I got to break this bond and break this bond and remake the H bond over here, remake the CH3 bond over there. But what for these complexes? Watch what I'm going to do. We've shown these are mirror images of each other, because the complex is optically empty. All right? Here's what I'm going to do. I'm going to take this single bond and break it, and this single bond and break it. I'm talking about these substituents on our nitrogen donor atom, which we have recognized to be carbon. Now, if I do that, you saw what I did. And here we go back to the substituted ammonia molecules, which we recognize to be mirror images and different, because they're not superimposable. All right? If I operate on this thing and take and break two bonds, not too strong, can't break it. Let's break this bond. Break this bond. Remake it. What I have just done is to turn this thing into that thing. Now they're not mirror images anymore. Now they are identical. I broke and remade any two sets of bonds. I don't care which ones you do. You can take the non-bonding pair off, blue, put it there, and there, and go back to the mirror images. Keep on going and keep on going and keep on going. So it appears that I did that with this, don't you think? Well, let's see how these compare now. All right. See, the rings are, so these are clearly mirror images of each other, yes or no? No. Are they the same? Let's try the test. And all these monodentate ligands here matched, here matched, here matched. But look what we got over here. Still not superimposable. and clearly not mirror images of each other. Are these complexes each optically active? Do they each contain a chiral atom? That nitrogen donor atom is still chiral. And are these clearly isomers of each other? They're compositionally identical. They're structurally identical. But are they the same? No. Are they mirror images of each other? No. What are they? They're called diastereomers. Diastereomers are isomers of each other. But not mirror images of each other. They're structurally identical. Practically speaking, geometrically identical. But they're not mirror images of each other. These are diastereomers. How do I begin to get familiar with this kind of stuff? I draw pictures and or make models. I don't have a choice. And organic chemistry is rich in this kind of stuff. That's why I show you. Because obviously, you now see this is also very much a part of coordination chemistry. Because if you use a chiral atom in a ligand that you use to make a complex, you made an optically active complex because one of the atoms you use to make the complex is chiral. Increases the stereochemistry of the system considered. Now, one last issue in brief. We talked about this, so this shouldn't be too difficult to zip through. Three-atom ring. How are the component atoms of this ring hybridized? Well, if you count sigma pairs, you're going to argue sp3. But you're going to find out in organic class, they're going to argue a hybridization scheme for this, which is different from sp3. Some people, I think, call it sp6. Whoop! Because this is just a game. Question. What happens to bond angles as I increase the p character of an sp-type hybrid? What happens to bond angle as I increase the p character of an sp-type hybrid? sp, bond angle is 180. sp2, 120. sp3, 109. So, as I increase the p character, what's happening to the bond angle? It's getting smaller. That's why they come up with this crazy sp6 for this three-atom ring, because sp3 hybrid likes 109.5-degree bond angles. This thing has got 60-degree bond angles. Clearly not bond angles which correspond to sp3 hybridization at all. And this is very reactive. This ring tends to open quite readily because this ring is not stable. Here, the bonding electron pairs, in order to be stable, have got to be right between the nuclei of these bond atoms. But when they have this triangular geometry, these bonding electron pairs are really close to each other. Do electron pairs like to be close to each other? No, they repel each other, which tends to open this ring rather readily. It's reactive and not stable. Upshot. You can't make any three-atom chelate rings, at least none that I know of. You can't make any four-atom chelate rings where one of the atoms is a middle atom, not that I know of. Maybe there are some examples. But how about five-atom chelate rings? Sure, we've already recognized that works. Ethylene diamine, right? Now, what about six-atom chelate ring? Have we looked at this before? Well, let's play one game with the six-atom chelate ring. Tell me. CH2, 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 NH2, NH2. And here's the metal. How are these ring atoms N, C, 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 N? The ring atom of the chelate, how are they hybridized? They're all sp3. What kind of bond angles are we looking for? 109.5 degrees. Now, if this thing is flat, how many degrees are encapsulated within? How many total degrees inside this ring if this thing is flat? How many total degrees inside the ring? 720. You did this in geometry class, didn't you? Triangle, 180 degrees. Square, 360 for a rectangle. Pentagon, 540. You keep on adding 180 degrees every time you add them to this planar thing. So here's 720. All right? Now then, 1, 2, 3, 4, 5. sp3 hybridized atoms. So I can take 5 times 109.5 plus, if this is a octahedral complex, 90. And see how close that comes to 720. Will I get exact agreement with 720? No, I won't get exact agreement with 720. But don't forget, let's put this together in just a second. And if I have a ligand like this, you see the 2 nitrogen atoms at the end? And the 1, 2, 3 carbon skeletal atoms? And all the skeleton atoms are sp3 hybridized? And because of free rotation, these non-bonding pairs can aim at the same position in space, and in so doing chelate me. But when they chelate me, do I get a planar ring? No. So guess what? Because the ring is not planar, I wind up with bond angles that are exactly those required, or pretty near so, by sp3 hybridized atoms. Because when I take and pucker a bond, pucker, you know, like this kissing activity, pucker, what happens to bond angles when you pucker? Straight. What happens to bond angle when I pucker? Like this. Bond angle decreases because these rings are not flat. Enough said.